All right, let's begin. So today we're talking more about use substitution, and tomorrow we're talking more about use substitution, okay? Tomorrow we'll actually see why it's called use substitution. So far, that's just a name that you have no idea why it's called that. There's a reason why it's called use substitution, but and we'll see that tomorrow. But before we get started, there's a quiz after class today, very similar to yesterday's quiz. Um, Yesterday's quiz was, or not yesterday, sorry, Tuesday's quiz was slightly easier than today's quiz is going to be, but it's still same principle, okay? All right, and then that's really the only announcement. Okay, so are there any questions about this singular announcement? All right. Well, then let's warm up with a use substitution problem. Let's find the indefinite integral of e to the x times 1 plus e to the x quantity cubed with respect to x. Okay, so as a reminder, we want to try to find, this looks like it maybe could fit the pattern of f, taking the integral of f of g of x times g prime of x with respect to x, right? And if that is the case, then really the only thing I need to find is an antiderivative of f, and this will just be big F of g of x plus c. So I just need to verify that this looks like this. I need to pick g just right so that we have the integral of f of g of x times g prime of x. Okay, so what do we think g of x should be? Well, it should be apparently, hopefully, it's inside some other function that is relatively easy to find the indefinite integral of, right? So is there a function in here that looks like it's inside some other function?
1 plus e to the x.
1 plus e to the x. Very good. So I'm going to make the guess. And again, with use substitutions, sometimes the guess is obvious and it's going to be right. Sometimes you're making a guess and you don't know if it's going to give you what you want. And that's fine. Integration is hard. Integration in general is much harder than differentiation. Okay. So I'm going to guess g of x is 1 plus e to the x. Then what is g prime of x? E to the x, very good. And so g prime, well, e to the x right there, that looks like g prime of x. So this, this looks like my f of g of x, right? So what is little f of x for us? Perfect, x cubed. X cubed. It's the outside function, right? The outside, we find the inside first, and then use that to say, well, what should the outside function be? Okay, so then I just need an antiderivative of little f. So what's an antiderivative of little f?
4x over 4.
Full,
X to the 4th over 4.
perfect, x to the 4th over 4. Very good. That's an antiderivative. And that's really all we need. We don't really need the general antiderivative. And so this, in the end, well, I want to take capital F, and I want to plug in G. So when I do that, oh, sorry about that, people here, all 20 of you. When I do that, I'm going to get, well, big F of G of X. Well, that's going to give me 1 plus e to the x to the 4th divided by 4 plus c. Okay. How can I check that this gives me the right answer? This is something that I forgot to mention on Tuesday. But the great thing about integration, indefinite integration is hard, but checking my answer is not easy, but it's easier than finding my answer. How can I check my answer? Yes, thank you, Saba. We can differentiate, right? If I differentiate this, I should get that stuff on the inside of the integral. And that is what you get here. You get 1 plus e to the x cubed times e to the x by the chain rule. So are there any questions about this? So this is what we did Tuesday. We just tried to find G, and we hoped that, we crossed our fingers and hoped that G prime exactly would show up. If we picked the right G, we would get exactly this pattern, f of g of x times g prime of x. Now, in real life, in situations in the real world, it's not always going to happen that you get exactly f of g of x times g prime of x. Okay? It's very rare that that would be the case. But a lot of the time, a surprising amount of the time, you're going to pick a g of x that looks like it should be right. And when you find g prime, you're going to see something in the integral that's almost g prime, but it might be off by a factor of 2 or 3. And that's fine, because if we look at the integral, well, what do we remember about the integral of a function times some constant? Well, I can pull that constant out of the integral, right? So if I'm trying to find g so that I get f of g of x times g prime of x, and I pick g, and my g prime is off by a factor of some constant, well, the idea is you're going to multiply by whatever constant you need to be there. I can't change, that would change the value of the integral. So I multiply on the inside and divide on the outside by that constant. Okay, that doesn't change anything. I just multiplied by 1, but then we will perfectly get that pattern that we need, f of g of x times g prime of x. Okay, and it's really shocking how often in real life this is all you need to be able to do really complicated integrals. Okay, so let's, the best way to see this is with examples. Okay, let's find the integral, the indefinite integral of x times 1 plus x squared to the 50th with respect to x. This integral would have been nearly impossible for us to do. We technically could have done it before by expanding 1 plus x squared to the 50th, and then we would have had 50 terms to integrate term by term. That sounds awful. Instead, we're going to do a u substitution. So I want this to look like, again, the integral of f of g of x times g prime of x with respect to x. I want to make this look like this general template, right? This general pattern. Well, what should we pick g of x to be, do you think? Yeah, g of x, again, that's the inside function. It looks like we have a composition right here. This looks like a composition of two functions. It's one function inside of another. So I pick g to be the inside function. And I hope that the derivative of g is somewhere else in this integral. Okay, so g of x I'm going to pick to be 1 plus x squared. Okay, then what is g prime of x?
2x.
2x, right? 2 times x. And really quick, what is f of x? The outside function.
X to the 50th.
50th, very good. All right, so we don't, using this g, we don't exactly get the pattern we need, right? Because this, using this g and this f, we would hope to get the integral of 2x times 1 plus x squared to the 50th dx, right? but that's not exactly what we get. We're looking at the integral of x times 1 plus x squared to the 50th. So the whole idea is, well, I'll make it look exactly like I want it to look. I want it to be 2 times x times 1 plus x squared to the 50th. So I multiply inside by 2. But again, I can't just multiply by something that's not 1. So then I'll multiply on the outside by 1/2. Okay. So when I do that, now I really want to find this, right? This is what I'm trying to find. But this, as we know, is just equal to 1/2 times, well, this integral here is capital F of g of x plus some constant, right? Okay, so what is capital F? Remember that's
Isn't that just x to the, is that just x to 51st over 50? Yeah, no, that's not it.
no, you're exactly right. That's exactly right. It's capital F is x to the 51 divided by 51. I add 1 to that exponent of 50, and then I divide by the new exponent. Okay, again, that's the power rule for integration. That's the exact opposite of the power rule for differentiation. Very good. So then I just use this big F right here. And I use G right there, okay? So I end up with the 1/2, again, 1/2 because that's what I need to multiply by to get that pattern exactly. 1/2 times, well, capital F is x to the 51st, so capital F of G of x is 1 plus x squared to the 51st divided by 51 plus some constant. And then this is equal to 1 over 2 times 51 is 102 times 1 plus x squared to the 51. And then this is something that really gets on a lot of calculus students' nerves, and it got on my nerves a lot when I was first learning indefinite integrals and that concept of integration. You could say that this is c over 2, but because c is just an arbitrary constant, most mathematicians just call c over 2. We just say that that is some other constant that we're also going to call c, okay? So c plays by its own rules. Most people, if you want to write c over 2, that's totally fine. I'm not going to count off any points. But most people just rename c over 2 as another arbitrary constant and call it c, okay? I get that that's annoying. I get that that's frustrating. It happens all the time. So I'm just letting you know in case you see it in real life. Okay? Let's check that this is indeed correct. So when we take the derivative of this, we're claiming that this is what we want. When I take the derivative of this, the dx of 1 over, I'm going to write it as 1 over 2 times 51 times 1 plus x, times 1 plus x squared to the 51 plus some constant. And really, again, you can think of that as a constant over 2. Well, I'm going to use the chain rule. The inside function is 1 plus x squared. The outside function is x to the 51st. And so when you go through and you use the chain rule, you're going to get 51 over 2 times 51 times 1 plus x squared to the 50th, which is 51 minus 1. and then I multiply by the derivative of the inside times 2x. Okay, so the 51 over the 51 cancels, and the 2 cancels with that 1/2. I'm left with 1 plus x squared to the 50th times x, which is exactly what we wanted to get. Okay. Very good. Questions about that? Okay. So that's really, I mean, that's the whole idea. Okay, so let's find another integral. Let's find the integral of cosine of 5x with respect to x. Okay, so again, this looks like it could be the integral of f of g of x times g prime of x with respect to x. And that would be equal to capital F of g of x plus some constant, if that is the case, right? Okay, so what is g of x here? What's the inside function?
Five x.
5x, very good. The inside function is 5x. That makes g prime of x equal to 5, right? The derivative of 5x with respect to x is just 5. And what's the outside function? Little f of x. Very good. Cosine of x. Cosine of x. Something I've noticed is some people say cosine times x. No, cosine is a function. It's cosine. You didn't say this just now. I'm just cosine is a function. Cosine of x. Okay. So if this matched the pattern perfectly, we would have, instead of just the integral of cosine of 5x, we would have this g prime in here. We would have 5 times the integral of cosine of 5x, right? But we don't. But if I multiply by 5 and then divide by 5, then we have exactly what we want. Okay. So then really, I'm looking at 1/5 times this stuff. Okay. Because now this inside integral matches this pattern perfectly, but I need the 1/5 out in front. So really we're looking at this, right? I multiply both sides by 1/5. Okay. Questions on this? Okay, what is the an antiderivative of cosine of x? Yes, thank you, Saba. It's sine of x. Really, you have two options, right? Your guess, you should have either thought, well, it's either sine of x or negative sine of x. But you only get a negative when you differentiate something with that starts with a c. So if I guess negative sine of x, then the derivative of that is negative cosine of x, and we don't have a negative here. Okay, so it's positive sine of x is an antiderivative, and that's all we need is an antiderivative. Okay, so I'm basically done. I plug in here, I get 1/5 times, well, capital F. So capital F, sorry, I should have written this down here. Let me erase this. Capital F of x is sine of x. So we get 1/5 times sine of, that's big F, sine of g of x plus some constant. And again, you can say this is 1/5 times the sine of 5x plus, I'm going to call c over 5, just another arbitrary constant. I know that's annoying. If you want to write c over 5, that's fine. But ultimately, it doesn't matter. Just like, that's an awful joke, like matters. Okay. Questions? This is entirely what the quiz, I mean, it's not these exact problems, but the quiz looks almost exactly like these two problems, okay? So, all right. So we actually did get to, I thought those examples would take longer, but you guys are excellent. So we actually are going to see why it's called a U substitution, okay? So trying to match up G and F is fine. What most people normally do is they normally let the inside function, they normally call it U. And this is why it's called a U substitution. It's as stupid as that. We usually call U G of X. Okay. Then when we do that, U is G of X. And so du, I want to replace G of X. So I want to get rid of G of X, and then I want to replace then also dx. If I'm integrating some new thing with respect to U, I need to change dx to du. Well, the way you do that, you take the way, this always bugged me as well, du dx. If I take a derivative with respect to x on both sides of U equals G of X, well, I'm going to get du dx on the left. On the right, I take a derivative with respect to x. That's just G prime of x, right? Equals G prime of x. And then you can think of the derivative on the left, du dx. Think of it as a fraction. And then you can move the dx over. Okay, and this tells you that du equals G prime of x dx. Now, du dx, the derivative of U with respect to x, is not actually a fraction. This is a way to help you remember when I change U, I also need to change, or when I change x to U, I also need to change dx to du. These symbols du and dx actually have very deep meaning that we won't cover even when we get to Calc 3. If anyone goes all the way through to Calc 3, we're not going to cover what du and dx actually mean. But you can think of them as just a tiny sliver of U and a tiny sliver of X. That's the way most people think of them, okay? So, but once we make this, it's called a change of variable, this U substitution, then we replace both G of X and dx in the original integral, and then we'll have an integral with only U's, okay? U's guys. So this is called change of variables, and it is called a U substitution as well. That's why most people call this U substitution. There is nothing special about the letter U. If you used W, you would call it a W substitution. If you used V, you could call it a V substitution. In general, it's a change of variables. The name of it doesn't really matter. Just know that we're integrating by substituting this complicated G of X for something simpler, okay? So we're going to see a U substitution using the letter U in action. I want to emphasize that we've been doing this. This is what we've been doing, and now I'm just showing you a way to kind of remember the method a little, I think, a little more simply, okay? So let's find the integral, the indefinite integral of x minus 4 over the square root of x squared minus 8x plus 1. Okay, so now we're just going to say U is, we're still going to call U G of X. It's still the inside function. It looks like we have a composition happening here. So what would be the function that's inside of another function here?
x squared minus 8x plus 1.
Good. X squared minus 8 times x plus 1. Then du. Well, du is the derivative of the right-hand side times dx. That's how you can think of it, okay? Another way you can think of it is what is just the derivative of u with respect to x? Well, what is the derivative of u with respect to x?
2x minus 8.
2x minus 8. Very good. Just take a derivative with respect to x on both sides. And then now, once you do that, now I move the dx over to the right. So I've got u is right here, right? This is u. We have what's left over is this x minus 4 dx. When I find du, I have 2x minus 8. So what do you think I should do to both sides of du? I want to have an x minus 4 dx, and then I can just make a direct substitution. So I'm going to divide both sides of this by 2. Okay, and when I do that, I'm going to get 1/2 du on the left. This is equal to x minus 4 dx on the right. And x minus 4 dx is exactly what I have left in this integral. Okay. So then this is really the integral. When I make my u substitution, I get the integral of, well, x minus 4 dx. I know that that is 1/2 du. So I'm going to write the 1/2 on the outside. du. That takes care of x minus 4 dx. And then divided by, what's the bottom? You guys tell me. What does that bottom become once I make my substitution?
Is it du dx?
No, we've taken care of the du, so we're done with that. But what haven't I used here yet? What's not making an appearance so far in this new integral?
Would it be 2x minus 8 to the 3/2 over 3/2?
2x. That's going to be, in the end, I think that's going to be close to what we need. But right now, I just want to know what goes in the bottom here. So right before, the bottom was the square root of x squared minus 8x plus 1. And then we said u is x squared minus 8x plus 1. So now in the bottom, I'm going to have the square root of just u. Okay. So I let u be the complicated function that's inside another function. Then I find du so that I know how to replace dx. Okay. And then I just replace du here 1/2 du with x minus 4 dx, or really the other way. And I replace the complicated x squared minus 8x plus 1 with just u. Okay. So if I rewrite this a little bit, this is 1/2 times the integral of u to the minus 1/2 du, right? So then this is equal to, well, what is this? The 1/2 is out in front. What rule do I use to integrate u to the minus 1/2 with respect to u? Yeah, exactly right. The power rule. I'm just going to use the power rule for integration. This is independent variable to a power. I mean, it doesn't matter that it's a u and not an x. It's still whatever we're integrating, whatever variable to a power, you're using the power rule. Okay, so I'm going to get, well, when I add 1 to minus 1/2, I'm going to get u to the positive 1/2, u to the positive 1/2. And then I need to divide by 1/2 plus some constant. And so when I simplify, I'm going to get 1/2 times 1 over 1/2 is 2u to the positive 1/2, still plus c. And this is equal to, well, 1/2 times 2, that cancels. I get u to the 1/2. And c divided by 2. Again, if you want to write c over 2, that's fine with me. I don't care. But more often, when you see people do this in real life, they're just going to write plus c again. Okay? Now, u substitution, I like to think of it as sort of changing languages. If someone asks you a question in English, but your native language is, say, Spanish, it might be easier for you to think of the question in Spanish, answer it in Spanish, but you wouldn't want to verbalize your answer in Spanish because the person who asked in English, right? You would want to verbalize your answer in English again. So when we make the u substitution, that's thinking of the integral in a more natural way, changing the variable so it looks much easier. But then when we give our answer, I need to give it in terms of the variable we were given. So we were given the question in terms of x. So I need to report my answer back in terms of x. Because again, if someone asks me something in English, I should answer them probably in English, right? So this is u is x squared minus 8x plus 1. So I replace u back. U is x squared minus 8x plus 1 to the 1/2 plus c. So, some points. I know that the du feels unnatural. It's definitely the most unnatural thing about this sort of changing from just trying to match the pattern to this new way of thinking of this in terms of a change of variable. But when you're doing definite integrals, it's easier. This u substitution is easier. And when you use u substitution, when you practice it more and more, this will feel more natural to try when you find du to just make multiply du by some fraction to make it match dx with whatever is left over perfectly. Okay. So do we have any questions about this? If you prefer finding the pattern and then matching up integral of f of g of x times g prime of x with respect to x, that's fine for very simple examples like this. Later, we might need to make like 2 u substitutions. It's totally possible that you might need to make multiple u substitutions, and then matching the pattern again and again is much more difficult than just saying u is equal to stuff and rewriting the integral in terms of u. Okay, so this is definitely a better way to think about the integral. So practice it. It'll come more naturally, I promise. We're going to do another example right now that for some reason I didn't move up to the top of the screen, but that's okay. All right, so find the integral of, the indefinite integral of 1 over theta squared times cosine of 1 over theta with respect to theta. Okay, so I need to find what is the function. Is there a function in here that's inside some other function, some sort of composition? And if there is, I'm going to let u be that inside function. So what do we think? Is there some function that's inside of another function here? Yeah, exactly. U is going to be 1 over theta. Very good. Then that makes du d theta. Well, 1 over theta is theta to the minus 1. So what's the derivative of theta to the minus 1 with respect to theta?
Negative theta to the minus 2.
Perfect. Negative theta to the minus 2, which now I'm going to rewrite as minus 1 over theta squared. Okay, so then that tells me that du, just multiply d theta over to the right. I mean, du is negative 1 over theta squared d theta. Okay, so looking here, I have u is on the inside of here. Cosine of u, I'm going to know how to integrate that. I have what's left over is 1 over theta squared d theta. I have du is minus 1 over theta squared d theta. So what should I do to both sides of du equals minus 1 over theta squared d theta? I want it to look like 1 over theta squared d theta. Currently, I have minus 1 over theta squared d theta. So what?
Multiply by negative 1.
Yeah, I'm going to multiply both sides by negative 1, okay? So this tells me, so there's still definitely a matching game going on, right? This tells me negative du is equal to 1 over theta squared d theta. Okay, and so now I plug in everything. All right, I have the integral of, well, I'll do just the u first. Cosine of 1 over theta, that's cosine of u. Okay, so the integral cosine of u. And then what's left over? 1 over theta squared d theta. Well, we know that that is negative du. Okay, so I'll put the negative out in front. Du. Okay. So this is what I was saying about languages. This is someone asked us a question in a kind of unnatural language for us. So the natural thing to do is switch to something that makes more sense. This integral makes it's a lot easier to do, right? What is the antiderivative of cosine of u with respect to u? Or the indefinite integral, sorry. Oh, we have it in the chat. Sine of u, yes, very good. Sine of u plus some constant. Okay, so this is negative sine of u. And again, if you want to write minus c, that's fine. It's an arbitrary constant. It doesn't matter if you multiply by another constant, divide by another constant, it's still some arbitrary constant. Okay. And then what's the last thing I need to do? Am I done? Did I finish this problem? Yeah, I need to substitute u back. Because again, if someone asks you something in German, you shouldn't answer them in English, you should answer them in German. So this is negative sine of u, again, was 1 over theta. Okay. Plus some constant. Das stimmt. That's German. Okay. So, and that's our answer. Do we have any questions about this? So some general guidelines for making a change of variables. You're gonna choose u equals g of x. It's still, you still want to try and recognize that pattern. What is g of x? That function that's inside some other function. Okay, it's usually best to choose the inner part of composition of functions. Okay, so for instance, we've done a lot of some function raised to a power. So like 1 plus e to the x raised to the third. Well, we picked 1 plus e to the x as u. Okay, will it always be the case that that's the best choice? No, that's what makes integration hard and weird, is sometimes some functions you need to do something slightly different. Okay, so then once you've chosen u, you compute du is just g prime of x dx. Or in general, g prime of your first variable, d your first variable, right? When we had theta, it was g prime of theta, d theta. Okay, then you rewrite the integral in terms of only the variable u. Okay, this involves replacing g of x with u, and then du with g prime of, or really g prime of x dx with du. And for that, you're going to need, that's where you need to do a little bit of massaging most of the time to make the right-hand side look like what's in the integral. Because most of the time, it's not going to be exactly g prime of x dx. Okay. But it will usually be off by some factor. Okay, then you find the resulting integral in terms of u. No surprise there. Then you need to replace u back into that general antiderivative that you found. Okay, so that you're asked a question in terms of x, you give an answer in terms of x. So, any questions about these guidelines? Oh, and check your answer. Yeah. Yeah. Yeah, it's still essentially the same thing. We're finding, so I mean, we're looking at the integral of f of g of x times g prime of x dx. Really, it's the same thing now, but now instead of just going straight to capital F of g of x, I let u equals g of x, and I get f of u, and then g prime of x dx is du. Then this clearly has an antiderivative of capital F of u plus some constant, and then you substitute u back. So we're sort of making a couple of intermediate steps. But again, it's definitely the better way to do this for later when we talk about more complicated integrals. Any other questions? So this one's a little more fun. Let's find the integral of sine squared 3x times cosine of 3x. This one's a little tricky. Why is it a little tricky? Who can tell me why it's a little tricky? Exactly. There's multiple inside functions, right? This is really the integral of sine of 3x squared times cosine of 3x dx, right? So, what should I make u here? we really kind of have two choices. And this is going to happen to you a lot. You're going to have multiple choices for what should you be. Well, let's say you make the initial guess of, I think u should be 3x. Well, if u is 3x, then what is du?
Three.
Yeah, it's just 3 dx, right? So that means dx is 1/3 du, right? I don't have a cosine of 3x anywhere in here, so I'll just solve for dx, because I will be able to replace this 3x and this 3x. So if I can just replace dx, then I'll have a new integral in terms of only u's. So let's substitute this. Then we're going to get, when I plug this in, well, this is the integral of, this is sine of u squared times cosine of u, and dx, that's 1/3 du. Okay. Now what should we do? What does this look like now? First, you should just ask yourself, do I know a function that just has this as its derivative? And the answer is no. You don't know a simple function that just has this as its derivative. So this is still an integral of some composite function, right? There's an inside function and an outside function, and then some stuff left over. What do we do when we have that? Yes, we make another u substitution. Okay. Now instead of using u, I'm going to use another letter because it's already in terms of u. So I'm doing a second u substitution. And so to be cute, I'm going to make a w substitution. Okay, so I'm going to say w is, well, what's the inside function happening here? Sine of u. Sine of u is being raised to the second. That's one function inside of another function. Okay, so I'm going to call w sine of u. And what is dw? Perfect. Cosine of u du. So then I plug this stuff now into this integral. So we're gonna copy and paste this using technology. Copy, paste. This is the integral that we're now making a w substitution. And so when I do that, I'm gonna get, well, the 1/3 is still out in front. I didn't change that at all. The integral of sine of u, that is w. So I get w squared, and then cosine of u du, that's exactly what we have left over in this integral. So that's just dw. Okay. Questions so far? Okay, so then this is equal to 1/3 times what? Oh, it's 850. I did not realize that. Well, power rule, right? W squared, I'm going to add 1. I'm going to get w to the 3rd divided by 3 plus c. So this is 1/9 times w to the 3rd plus c. But then again, I can't give my answer in terms of W when I was asked something in terms of X. So this is equal to 1/9 times sine of U cubed plus C. And again, I was asked in terms of X, so I need to also replace my U. So this is finally equal to 1/9 times sine of U was 3x to the third plus some constant. Beautiful, amazing U substitutions. Okay, amazing. Perfection. All right, so if anybody has any questions, you can stick around and ask me. I'm going to open the quiz up here in a few minutes, so make sure to get that done before the end of the night. And I'll be available via email if you do have any questions about that. Okay, so thank you all for being here. I'll see you tomorrow, and we'll pick up from here. Thank you.
Thank you.